Now for our last part of our discussion, let's have Doppler effect. Have you ever heard an approaching fire truck and noticed the distinct changes in the sound of the siren as the truck passes? Such phenomena were first identified in 1842 by the Austrian physicist named Christian Doppler and referred to as the Doppler effect. It is a change in frequency or pitch of the sound detected by an observer because the sound source and the observer have different velocities with respect to the medium of sound propagation. Now let's go to the simulation. So this simulation will illustrate the Doppler effect, and we have here 5 scenarios. So for our first scenario, the observer and the source of the sound, which is the black one, are both stationary or has no velocity. And by the way, the observer is this red one. So you can see that the observer perceived a constant amount of sound intensity or heard a constant frequency. For the second scenario, now the observer is moving while the source is stationary. So as it moves towards and as it go away from the source of the sound, the frequency changes. For our third scenario, this time, the source of the sound is moving toward the observer and getting away. And so you can see how the sound intensity or the sound wave is changes as the source is moving. For our fourth scenario, both observer and the source of the sound is moving. Now, for our last scenario, our observer is stationary while the source of the sound is moving at high speed. So the changes in frequency and the velocity of the observer and the source of the sound can be described by these formulas. So we have here 5 formulas. So for the source are moving and the observer is stationary, we have here this formula, where FO is a frequency heard by the observer and Fs is a frequency emit or released by the source. And Vs is the velocity of the source, while V is the velocity of the sound in air, which is equal to 343 meters per second. In these formulas, where the observer is moving and the source is stationary, we have here Bo is the speed of the observer. And for the case that both observer and the source of the sound are moving, we have here the formula. Now let's try to solve this problem. A high-speed train is traveling at a speed of 44.7 meters per second. When the engineer sounds the 415 Hz warning horn, the speed of the sound 340 meters per second, what are the frequency and wavelength of the sound as perceived by the person standing at the crossing when a train is A approaching and B leaving the crossing? So for our first scenario, wherein the train is moving or approaching to the observer, we will use the formula FO is equal to Fs times 1 all over 1 minus Vs over V to get the frequency heard by the observer. Then later on, we can solve now for the wavelength. So substituting the value of Fs which is Fs is for 515 Hertz, and Vs is the speed of the train, which is 44.7, and V is the speed of the sound, which is 343. We can solve for Fo, which is equal to 477 Hertz. And to get the wavelength, it is equal to the speed of the sound over the frequency heard by the observer. Therefore, it is equal to 0.719 meter. Again, to get the wavelength, we use the velocity of the speed of the sound, which is 343 divided by the frequency heard by the observers. And for our second scenario, which is staging the crossing, to get the frequency heard by the observer, it is equal to Fs times 1 all over 1 plus Vs over V. And substituting the value of the frequency and the velocity of the train and the velocity of the speed of the sound, we can get the frequency heard by the observer, which is equal now to 367 Hertz. Therefore, the wavelength heard by the observer as the train is leaving the crossing is equal to 0.935 meter. Okay, for our second example problem, a speedboat starting from rest moves along a straight line away from a dock. The boat has a constant acceleration of 3 meters per second squared. Attached to the dock is a siren that is producing a 755 Hz tone. If the air temperature is 20 degrees Celsius, what is the frequency of the sound heard by a person on the boat when the boat's displacement from the dock is 45 meters? So we are looking for the frequency heard by the observer as the observer is moving away from the source of the sound, wherein the source of the sound is the horn or the siren that located at the dock at a stationary position. To get that, we will use the formula of FO is equal to Fs times 1 minus BO over B. So we have the value for the frequency of the source, which is 755 Hertz. And the value of the velocity or the speed of the sound, which is 343 meters per second, which is constant. So we need to look for the velocity of the observer. So we need to look for BO. So using our equation, or in the equation in our kinematics, we can solve for BO by getting the square root of initial velocity of our observer squared plus 2 times the acceleration times x. So the initial velocity of our observer is 0. And the acceleration of our observer is 3 meters per second squared. And he is located at 45 meters. Then we can solve now for BO. And doing so, substituting the value for the value of the acceleration and the displacement, we can get now the value of BO. And by getting the value of BO, we can use it to apply in our formula in solving the frequency heard by the observer. Therefore, our final answer is equal to 719 Hertz. Now, so for your test your understanding, solve this problem.